As I mentioned, this is the last of our topics. The theory behind this is pretty easy, and I think, like a lot of the other stuff we've done in here initially, you'll find it pretty straightforward and simple, and then, of course, it will ramp up. But I've got some very good news for you later in the slideshow, which we'll get to soon. It's better when you turn it on. There we go. So we're talking about antiderivatives. What do you think an antiderivative is?
The opposite of derivative.
It's the opposite of derivative. You can think of it as like an inverse function, even though taking a derivative technically isn't really a function. It undoes the function or undoes the process of taking derivatives. You've taken so many derivatives that this concept should be nice and easy. The problem is your brain is so set on derivatives that now I'm going to ask you to think differently, and when you have to do both in the same problem, which you will, it's going to get a little confusing. So, here we go. We're going to talk about something called a general solution of a differential equation. There's a lot of words in there that don't make any sense to you, but we'll get to it eventually. We're going to talk about an indefinite integral, and we're going to learn some new notation. I've got a new symbol for you today. I got a couple new symbols for you today. This will be fun. We're going to talk about how to take a basic integral. So an integral is the process of finding an antiderivative. Antiderivative is a noun, and integration is the verb. You can use integral and antiderivative interchangeably. We'll get to that later. And we're going to look at the difference between a particular solution and an infinite number of solutions. So I got a really simple question for you to start. So we're keeping it simple here, the KISS method. Let's suppose I've got a function f of x, which is 3x squared. There is some function that when I took the derivative of that other function, I got 3x squared as an answer. You understand the question? Yeah? What's the answer?
X cubed.
Say it loud, say it proud.
X cubed.
X cubed. Okay? So now that you know the answer, for those of you that looked a little confused, it should make sense. If we started with the function x cubed, when you take the derivative of x cubed, you get 3x squared. Now I'm asking you to go backwards. So instead of going from f of x to f prime of x, we're going to go backwards, and our notation for that will be a capital F. So now we've got capital F, lowercase f, f prime, f double prime, f triple prime, etc., etc., etc. Okay. So all we did is put the machine in reverse for a second and pop out that answer. Next question, however, are there any other functions that would satisfy this condition? Daniel?
X cubed plus 5.
What's the derivative of x cubed plus 5? 3x squared. Good. Are there any others? Say again? Plus any number. So how many functions satisfy this condition? Infinite. Good. Okay, so that infinity thing gets us to something, we did that already, so there's 7 and -2. We get to something called a family of antiderivatives. There are an infinite number of solutions that satisfy that initial condition that when you take the derivative of it, you get 3x squared. This becomes a problem. Kind of. But we have a solution for it. Now the first thing is, how do we denote that? How do I show that I know that when I take the antiderivative of 3x squared, I get x cubed plus some number? And that number can be anything. Obviously, I can't list all those numbers. So we have some notation that will allow you to demonstrate that you understand there's a ton of different answers here. And that is, we use the letter C. Capital C, by the way. That thing is called a constant of integration. And it's a big deal. When we get to the point where we're looking at AP questions that involve integration, and you'll recall that AP questions are worth 9 points, it is very common for one of those points to be given if you just remember to put a plus C at the end of your integral. Because there's a big difference between it being x cubed or being x cubed plus 7. Or x cubed plus c. Plus c says, there's a whole bunch of different answers here. Plus 7 is one particular answer. And that's where we get in the idea of something called a general solution or a family of antiderivatives versus a particular solution. And we're going to make that distinction in a couple minutes. Okay, any questions so far? Is that a fairly easy concept? Audience participation part of the program? Yes. Okay, we're just going to go in reverse. Sometimes it'll be a little trickier, but we'll get to that later. And you'll see that it's not as bad as you think it would be. For this one, all I did is I changed the notation a little bit. Instead of doing f of x, or doing dy dx, or doing y, I started with my function being y prime. So before we do this, let me ask you a question. What's the derivative of y prime? Not a trick question. What's the derivative of y prime? Y double prime. Okay, good. What's the antiderivative of y prime? Y. Good. Okay, so we got this idea of going backwards, right? The derivative of y triple prime would be y quadruple prime. The antiderivative of y triple prime would be y double prime. So it's just, again, putting the machine in reverse. So if I'm solving for y, when I take the integral of y prime, I'll end up with y, which will give me my original function. What's the antiderivative of x squared? Again, phrasing the question differently, what function, when you take the derivative of it, will give you x squared? Allie,
1/3 x cubed plus c.
how'd she do? Make sense? Well, there's an easy check. Is she right? Again, audience participation part of the program. Is she right?
Yeah.
How do you know?
I mean, if you derive it, you end up.
Yeah, you take the derivative of her answer, 1/3 x cubed plus c, and you end up with the exact function we're looking at. Okay, and you went with plus c instead of some other number, right? Could you have added a different number?
Yeah.
Yeah, she could have made c whatever she wants, but she went for the general solution. The general solution will have a plus c on it, denoting an infinite number of possibilities. Later on, we'll get into what's called a particular solution, that one possibility. This graphic is an example of 6 different answers that would satisfy the condition. You have to trust me on this one. All of those 6 colors are the exact same graph. They don't look like it because of the nature of the picture. But if I drag that orange one up on top down to the blue one, they would match up exactly. So the only thing the plus c does is slide the answer up and down in the graph. Why those 6? Because I just picked those 6. Just to show you how that, graphically, the answers look. It's all x cubed over 3, or 1/3 x cubed. We're just sliding it up or down because you remember your translations from pre-calc or algebra 2 whenever you did those. Now, let's get into some notation. Fancy new symbol here. I've looked for years to figure out what that name of that thing is, and as far as I know, it has no name other than the integration symbol. It looks like an S, and you're going to have to practice this a little bit, because some of you are going to do your integration symbols all fancy like. Some of you are just going to do that. Okay. You're going to have to practice this. Something that makes it clear that it's not an S, it's not a J, it's not a treble clef. Is that what those things are called?
Yeah.
One that looks like,
It just doesn't look all like that.
is that something like
That's
that?
an ampersand. Yeah.
Which is like an ampersand, right? But an ampersand, I think, is going like the thing on top of a Cheerios box.
Well, an ampersand is like an E and a T,
Oh, I did it.
like combined, because that's like some at.
Okay.
So, I don't know how that helps, but yeah.
I understand. Okay, so that's the integration symbol. And notice again, we're going backwards. So just for those of you that are visual learners, we're adding a new element to this, and that is we're saying now we're going to start with capital F of x, And going down, get out of the way. Okay, going down this way is derivatives. Derivatives. And then f prime of x, f of x, capital F of x. This would be integrals. No, same exact functions, same exact values, it's just a different process. You'll also notice we've got the plus c on there because we're talking about a general solution. So we want to outline all the different possibilities that you can get from that function. That thing that you're taking the integral of, that thing that you're finding the antiderivative of, is called the integrand. And you see that little dx floating there. Many of you are going to fight me on this. That little thing seems useless, but it is very, very important. That thing is called the variable of integration. It tells you what the variable is in the problem. That seems ridiculous right now, but be patient. That thing is the antiderivative, and then, as we mentioned, that's the constant of integration. I probably should have had another one for the integration symbol, but I don't think you're going to confuse that with anything. Okay. You'll see at the bottom there it says the term indefinite integral is synonymous with antiderivative. They're the same thing. Later on we'll talk about a definite integral, but you got some time before that happens. These are indefinite integrals because you're taking the integral of a function and getting another function. So that other function is called the indefinite integral. Okay, we good or am I going too fast? We're all set? Excellent. Okay, so basic integration rules. Just like when we did derivatives, we start slow and we start building up. How do we take an antiderivative? Is there a way that we can create a formula to take an antiderivative? What do we do with trig functions? How do I handle, dare I say, the quotient rule, or the product rule, or the chain rule, all those other fun things we did in derivatives? We're going to go through the exact same process with integration. That's what we want to do. Now, I changed things a little bit here, because notice if I go back this slide, I had f of x, taking the integral of f of x and getting capital F of x. In this one, I just changed the notation. I'm taking the integral of f prime of x and getting f of x. We good? Okay. Now, what happens if I take the derivative? And we need to talk about this because there's two different cases here. In that second rectangle, what am I doing first, the integral or the derivative? The integral, correct. Okay. So when I take the integral of this f of x, I'm going to get capital F of x plus c. Then I take the derivative. What's the derivative of c? 0. Right? Because c is a constant, and we know from taking derivatives that the constant will disappear. Which is why we get f of x. Okay? Is everybody with me? Now, we illustrated that earlier on when Allie gave us her answer of 1/3 x cubed, and we looked at all the other plus c possibilities. All of those, no matter what c was, when you take the derivative, you end up back at that x cubed or x squared that we were looking for. The same is true here. It doesn't matter when I take the integral what c becomes, because when I take the derivative, the c is going to disappear. Okay, you good so far? Hold your question 1 second. Now, why is this important? Because what if we do it in a different order? What if I take the derivative first, then take the antiderivative? Which I've got. slideshow all confused. Let's do this, I'll come back to it. I lied. What if I do this in a different order? If I take the derivative of f, oh, it's right up there on top. You're an idiot, Reedy. If I take the derivative of f, I get f prime. What's the antiderivative of f prime? F plus c. So there's going to be a c term there. If I do it in the other order, the c term disappears. Okay? So the reason I mention this is that people have a tendency to see this relationship and think of them as like inverse functions and just always tell them the answer is f of x. But the order that you do that in is relevant. Because again, anytime you take an antiderivative, you're going to have a plus c at the end of it. Okay, does that make sense? Sorry, I'm running around like a fart in a windstorm today. So we did this already to get that. And I don't remember what I gave you in the slideshow, but I'd like a general rule. How do I take the antiderivative? Well, Allie, let's put you on the spot. I gave you x squared before, right? How did you know the answer was 1/3 x cubed?
Because 3 times 1 is 1.
Beautiful. Okay, so if I gave you, let's see. If I gave you, let's go with x to the 7th. Could you tell me what the antiderivative of x to the 7th is?
1/8 x to the 8.
1/8 x to the 8th
Plus c.
plus c. Very good. Okay, good. Everybody agree? Okay. Allie, what if I give you x to the nth?
1 over. Wait, is that 9?
That's an n, yeah, n as in narwhal.
Oh. 1 over n plus 1 times x to the n plus 1.
You said 1 over n plus 1 times x to the n plus 1, and of course plus c.
Yeah.
Is that right? Does it fit the model in red? Does it fit the model of x squared? Okay, last question, then I'll leave you alone. Can you put that in English? Let's suppose I grab some schlub out of the hallway and we try to teach them how to take an antiderivative with no previous knowledge. What would you tell them to do to x to the 7th?
You add 1 to it and then divide them by that number plus 1.
Yes? Beautiful. Let's give it up for Allie. Well done. Okay. So she just explained to us the rule for taking an antiderivative. Take the exponent, raise it by 1, and another way to phrase it that might help is multiply by the reciprocal of that new number. Or 1 divided by that number, same thing. So since our function is x cubed, you raise it by 1 to 4, and then multiply by the reciprocal of 4, so you get 1/4 x to the 4th. Now, the good thing about this is if you're not sure, you have a very simple checks and balances. If I present this argument to you and I say that the antiderivative of x cubed is 1/4 x to the 4th, that was weird. How do you check to see if it's correct? Take the derivative. What's the derivative of 1/4 x to the 4th? X cubed. Okay. Yes, sir.
What if there's a number? Does that change?
Ooh, great question.
Does that make that number?
Everybody hear that? What if there's a number in front?
But you still add the exponent, then you multiply that number by the reciprocal of
Good.
the n.
Liam, I'll answer your question with another question. No, the other Liam.
Oh.
Let's suppose I gave you 7x squared. What's the derivative of 7x squared? 14x. How did you do that?
I multiplied the
You've done it so many times now you don't even realize what you're doing.
No, I did. What's the number in front? Oh, I don't know.
Coefficient.
Coefficient. You multiply the coefficient out.
Correct. I'll offer you an alternative answer. Couldn't you also do this? Take 7 times the derivative of that thing?
Yes.
You see where I'm going with this? So if I wanted you to find the antiderivative of 7x cubed, wouldn't that be the same thing as 7 times the antiderivative of x cubed?
Yeah.
Yeah. And we're actually going to get to that, so you jumped the gun a little bit. We're going to get to that in a minute.
I forgot.
Yep. Okay, because we have to look at a couple different scenarios. What if it's not such a pretty polynomial? What if the dreaded trig stuff shows up? How do we handle that? We got a lot of different things to talk about, but I just want to make sure that everybody's good on the basic idea of taking integrals. Just like taking derivatives, you're going to do this so many times, you're going to want to screen. But again, raise the power by 1, multiply by the reciprocal of that power. Okay. And then don't forget your plus c, because we're doing indefinite.
What about 1/4 x 4? Why doesn't that have a c?
Say again, I'm sorry?
Shouldn't that have a c in 1/4?
It should have.
Yeah.
Yep.
Okay.
Yep. I have failed you as a teacher.
It's okay.
I'm sorry. Everett wouldn't have made that mistake. He probably would have actually. Would Hernandez have made that mistake? Would she have left out the plus c there? Oh, okay, good. So we're all in the same boat. Because it's flashing, you know it's really important. Why is it really important? Because it's the basic operating method that we're going to use to find antiderivatives over and over again. It's just like when we did the power rule, not the product rule, the power rule way back when in September. You've done that so many times now you don't even think about it anymore. The same is true with this. And I kind of spoiled the fun before, but you will be happy to hear there is no product rule, no quotient rule, no chain rule for integrals. They simply don't exist. I'm not trying to snow you with some like, oh yeah, but there's these things. No, just flat out. Those don't work in integrals. All we're going to do is take antiderivatives. That's it. There's no other sneaky rule. Well, there's one other sneaky rule to learn, but we'll get to that later. But you don't have to, again, it's flashing, so it's got to be important. That's enough to give you a seizure. Now, you've seen this in red, yes? You've all seen the screen. You've seen it flash. But you know what a couple of you knuckleheads are going to do? You're going to try to apply the product rule, the quotient rule, the chain rule to integrals. Don't. Okay? They just don't happen. Here's a nice little summary chart. And I want to talk about a couple of these things. You've seen all of this before. There's nothing new up there. I just presented it to you in a different format. For instance, if you look at this thing going backwards, by backwards I mean you do it this way. If these are integrals, int, then this would be a derivative. And you know this already. What's the derivative of the natural log of x? 1 over x. What's the derivative of e to the x? E to the x. What's the... But, you know, we did that. The same is true with these inverse functions. I'm sorry they're there. We need to talk about them. Icky. You know that the derivative of sine is cosine. You know that... Oh. Now we got a minus sign popping up. So this is going to be a little confusing. Dealing with sine and cosine. You know that the derivative of sine is cosine. You know that the derivative of cosine is negative sine. But now we're going backwards. So I have this stupid thing that I learned. If you don't want to use this, great, but I can't get it out of my head, and it helps me remember this idea of this little trig guy I have in the corner. For me, what I struggled with is where does that stupid minus sign go? I know that when I took an integral of one of those two trig functions, one of them has to have a minus sign. And I wasn't a big memorizer, so I struggled with that until I had a professor show me this stupid thing. And I'm almost embarrassed showing it to you, but I will because maybe it'll help you, because it definitely helps me. Let's suppose I want to take the antiderivative of sine of x. Well, I turn the integral symbol into a golf club, and I turn the dot in the I into the golf ball. It's a stretch, but again, it works for me. When I use the golf club to hit that golf ball is going to travel very fast. Yes? How fast? So fast, in fact, that I'm not going to see it. It's just going to be a blur. And I remember that the derivative or antiderivative of sine is cosine. I know that inverse relationship occurs. The derivative of sine is cosine. The derivative of cosine is sine with a minus sign thrown in there somewhere. Okay, so that stupid golf thing helps me memorize or understand or remember which of the functions, when I take an antiderivative, has a minus sign on it. Now, I'm not stupid. I know that most of you already have burned into your brain that the derivative of cosine is negative sine, and therefore that's where you put my... But again, if this helps one or two of you, I've done my job. Questions so far? Not too bad, yes? Okay, now, how can we ramp it up? Well, we're not going to that much, except we're going to have to look at situations like Liam outlined. What if it's not just a pretty simple polynomial like x cubed or x squared? How do we handle it? How do we handle it when there's a coefficient out in front of it? How do we handle it when it's got a whole bunch of stuff mixed into one problem? What if it's not a polygon, that kind of stuff? And that's all we're going to talk about for the rest of the period. Not the rest of the period, but the rest of the slideshow. Okay, so I have a function. I want to take the antiderivative of it. Just like if you were taking the derivative of this, you break it into pieces. So what I want to do initially is that first step. I want to take the antiderivative of this function made up of three parts. So instead, I'm going to break it into three separate parts. And again, you did this when we talked about derivatives so much now that you probably don't even remember doing it, or you don't even think about it anymore. And then conveniently enough, based on Liam's question earlier, I move these numbers out in front because they don't matter, and then I just do those antiderivatives. So, we've done this already, but I'll ask, what's the antiderivative of x cubed? Okay.
1/4 x to the 4th.
Good. Times 8 would give me 2x to the 4th. Do you agree? Good. All right, let's stay with you, Nathan. What's the antiderivative of sine?
Negative cosine.
Good. Stupid golf thing. Minus. What's the antiderivative of 1 over x?
Natural log of x.
Technically speaking, we need an absolute value bar in there, but yeah. Yes, you're right. Good. Okay, done. When we get into these problems wholeheartedly, are you going to then consciously think, oh, I have this scary function. I need to break it into three parts. I need to move the numbers out in front. No, just over practice, you're going to eventually get to the point where you do raise 3 by 1 is 4, 8 divided by 4 is 2, 2x to the 4th. Golf thing for the sine, leave the 7 out in front, and you're going to remember that the derivative of a natural log of x is 1 over x, so therefore the antiderivative of 1 over x would be the natural log of x. Oh, yep. And look at that. Plus c. So there's a whole bunch of possibilities here. Now, you might be saying to yourself, well, wait a second. There's 3 integrals up there. Shouldn't there be 3 c's? Should there be 3 c's? Maybe. Good safe answer. Well, what's c plus c? C. What's c plus c plus c? C. So, technically speaking, yes, there should be 3 c's, but we know that I can just combine them into one big honking c. Be done with that. Okay? Questions? We're okay? Lovely. Oh, let me get rid of this. Whether you find this helpful or not, it's entirely up to you, but for some of you that it could help, again, I wanted to go through this. You've done this already with derivatives, so again, we're seeing a repetition of what we're doing. Take your original integral, rewrite it. Now, what does it mean by rewrite? Well, sometimes you will have a part of a function that's represented as, let's say, 1 over x squared. And when we were taking derivatives, you change that 1 over x squared into x to the negative 2. You might want to do that for this too. So for instance, in my example here, if I asked you to rewrite that before taking the antiderivative, what would you change? Who's talking? Is that you? What would you change?
I change the 5 cubed root x to x.
Beautiful. Would you change anything else?
You change the 1 over x to x.
Beautiful. Okay, take the antiderivative. I'll wait. In case you're wondering, yes, I did get a new Stanley for Christmas, and yes, I did get a Batman straw top. Remember, you're adding 1. So 1/3 plus 1. Not 2/3. 4. Gabby and Rosie. Oh, Kush isn't here either. Where's Kush? Anybody know? Hey, thanks, Captain Obvious. Oh, says he's in prison. That's not good. Okay, we good? I didn't have the answer up there. What's the answer? Maya, welcome to class. Let's put you on the spot. What do you got? It's okay. The worst that can happen is you're wrong, and then we'll just point and laugh at you.
Well, I couldn't figure out like how did it do the first 12x cubed 4 and then like try to divide by 5. Just 12.
So then how would you write it?
Yeah, I don't know.
Well, what would the x value be? X to the fifth. So what'd you do with the 5 then? You would divide it into 12, right?
Yeah.
And you're upset because 5 doesn't divide nicely into 12, right?
Yeah.
So then just write it as 12 fifths.
Okay, yeah.
Okay, what about the other two?
Wouldn't it be like 5/4 would be 1/3,
Keep going.
and then like 1 over x was like plus 3.
You missed a couple components. For the most part, you're good. So again, let's keep it simple. Raise the exponent by 1 is 5. Multiply by the reciprocal, 12 fifths x to the 5th. Minus. Now, depending on how good you get at this or how much you see it, I could just leave the 5 sitting there for a second and do the antiderivative of x to the 1/3. So as Maya said, if x to the 1/3, you add 1 to that, you get x to the 4/3. Okay. So I got x to the 4/3 here, but I need to multiply by the reciprocal of that, 3/4. And then Maya, you said you wrote this as x to the negative 5?
Yeah.
Raise it by 1.
So x then -6 or -4.
There you go. X to the negative 4th. Multiplied by the reciprocal would be negative 1/4. Whoop, there's a plus in there. Oh, thank you. Yeah. Got a plus c. And then I would clean this up. 12/5 x to the 5th minus 15/4 x to the 4/3 plus, nope, I lied, minus 1/4 x to the negative 4 plus c. If you wanted to write that as 1 over x to the 4th, you can. You don't have to. Good. And you see the 4 parts of that. We have the original integral. We rewrote it. We took the integral of each part and then simplified it to get our final answer. Okay? We good? All right, let's go back to this guy. I'm going to jump way back. I want, where's my picture? This one. Okay. So we know already that when we take the antiderivative of x squared, we get 1/3 x cubed. And I have, as I mentioned, 6 pictures there of all the possibilities. Suppose, instead of looking for a general solution, I wanted to get an answer that matched one of those colors. Let's say the green one. So I want you to take the antiderivative of x squared, but when you're done, instead of having a plus c on the end of it, I want it to satisfy the shape of that green curve. In other words, I want it to pass through a point. And in fact, if you look at the picture, the easy point to pick would be 0, 1. Are you with me? So the only thing that differentiates those 6 functions up there is the points that they pass through. If I want to narrow it down to one particular, and it's called a particular solution, I just need to give one more chunk of information. And that other chunk of information is, well, what point do you want it to pass through? How high above the origin do I want my new function to be? Do I want it to be up at 3? Do I want it to be up at a gabillion? Wherever you want it to go. And that's our next transition, is going, instead of a general solution with all possibilities, I want one particular solution. And that requires an extra chunk of information in the problem. Oh, yeah, I'll skip this and come back to it. Okay, so general solution, we've done that already. I'm not going to do it again. You can rewrite that as x to the negative 2, take the antiderivative, yada, 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 blah, 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 blah. Okay, but now I'm giving you some extra information. When I take the antiderivative of capital F prime of x, I will get a function with a plus c, but I don't want that one. I want this particular solution that passes through this point. By the way, just for giggles, what is that point? 1, 0 or 0, 1? 1, 0. Okay, good. Okay, so what does this mean? All right, well, here we go. I'm going to take the antiderivative of f prime of x dx, which, by the way, will give me capital F of x plus c. Okay, so we'll do that in a second. That's the antiderivative of x to the negative 2 dx, which is negative x to the negative 1 plus c. And that would equal y. Okay, y or f, actually, we'll use the proper notation here. Get rid of this. We'll use capital F of x. All right, you with me? Nothing new there. All I did is take an antiderivative. I haven't used this chunk of information yet. In other words, this is an infinite number of possibilities because it's a family of antiderivatives. How do I figure out what C is? Right? Yeah. Plug and chug. Put 1 in for x, put 0 in for y, solve for c. Go ahead, I'll wait. What's it equal? 1. Therefore, in a lovely shade of blue, f of x is equal to negative 1 over x plus 1. The red gave us a indefinite integral or a general solution. The blue is the particular solution. Only one possibility there. You can't do the blue unless you have some initial conditions. Questions? Make sense? Yes? Okay, good. Let's go back to this slide then. I talked earlier about that pesky little dx there. It has a lot of names. Differential, the d term, the dx term, whatever. The constant of integration is the c term, but that dx is important, and a lot of you will forget about it in your integrals because it doesn't seem to do anything. But when you've been doing this long enough, and as we delve more into this, you'll understand how important it is. So in the one to the left, what's the variable in that problem?
There are two. The very?
No, there is only one, and that's why we're doing this. So again, on the left, what's the variable? X. Okay, good. And that's the purpose of this dx. What the dx says is, come on. There we go. Okay. The dx tells you that your variable is x. And if your variable is x, what's the antiderivative of capital P?
X raised to p.
Nope.
Is it just the other room of B?
Nope. Maybe it's a good thing I'm going over this.
Is it 1/2 x squared?
Nope. Ellie?
Never mind.
Come on. What do you got? What are you thinking?
I was thinking 1, but then that didn't sound right.
Nope. No? Okay, let me ask you a question.
It's a function.
Not a trick question, simple question. What's the answer? 2x. We're all good, yes? Any problems? Okay, good. Any ideas?
Zero.
It would be 0. Why, Dunk?
Well, because the derivative of like any constant is 0, no?
Right, so when we were doing derivatives, we learned in this notation that is our variable. In this problem, x is our variable, and so we take the derivative like we take the derivative of everything else. When we get to this guy, x is still my variable, but I've got a z sitting there. By the way, Maya and Anthony, that my notation, that's a z raised to the second power. Okay, these are my z's, this is a 2. I apologize.
Got it.
Okay? Everybody good with this idea? Now take it backwards. If I get rid of this, and I take the antiderivative of p, where x is the variable, what's my antiderivative? Now, before you answer, think of it this way. What if I rewrote it like this? What's the answer? Not 2.
It's 2x.
2x. Okay, does everybody see that? Okay, if I take the derivative of 2x with respect to x, I get 2, which is exactly what I'm looking for there.
It's plus c, right?
Thank you. Okay, are we good? Does that make sense? So therefore, what would be the antiderivative of p dx? Px, good, plus c, again. Okay. Now, we jump over to the right side, and we take the antiderivative of this. What's the variable? P. So if P is the variable, what's the antiderivative of P?
One plus six.
No.
Well, wait.
What's the exponent on P?
Zero.
What's the exponent on P? 1.
Wait.
So what's the antiderivative of P to the first power? 1/2 P squared plus E.
Plus E. But
Some of you look very confused.
right. Well, doesn't
What's the matter? Are you talking?
the DP.
What about the P?
What was the DP though?
It goes
Oh,
away.
that's just-
Yeah, it's just there to tell you what the variable is.
Okay. Okay.
This doesn't happen a lot, but you'll remember when, again, going back to derivatives, remember we were strolling along, everything was great with derivatives, and then all of a sudden I brought in that pesky thing called implicit differentiation, where all of a sudden we were starting to take derivatives with respect to x and y. This is similar to this. It doesn't happen very often, but I'm trying to illustrate two things, and one is how this works, and number two, the importance of this dx or this dp. When you're writing integrals, when you're writing antiderivatives, you're going to get in the habit of either moving too fast or getting lazy, and you're going to write integrals, and I'm just as guilty of this as anybody. Whoa. You're going to write that. And that's sloppy. 99% of the time in here, it would be okay. When you get to the AP test, not okay. You've got to include this dx here for every integral. Okay, Leo.
So that means you can't have more than one variable, right? In an integral.
You can, but not in this class. There are classes called multivariable calculus.
Oh, that's a multivariable calculus. That makes
Yeah.
sense. Okay.
That's where you're taking the derivative of a function or an integral of a function where there's more than one variable and both of them are considered variables.
Yeah. Okay.
Yeah, you don't want to do that.
Yeah.
All right, are we good? I feel like we beat a dead horse here. Is everybody with me? Again, this comes up very little. What's more important is you understand the basic integral techniques we've done so far. Okay. And then we did this already. Doink, 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 doink. Okay. That's the same answer we got, right? Okay, good. This process of finding the particular solution is also known as a differential equation or a diffie-q. And why they have so many descriptions for the same thing, I don't know. It gets so confusing when you call it an antiderivative, an integral, an indefinite integral, and all this other garbage. The same thing is true here. Well, what do you want me to do? Am I finding a particular solution or am I doing a diffie-q? Well, they're the same thing. Okay. There's a function and an initial condition. When it says solve the differential equation, it means find the function f of x that satisfies those two conditions. That f prime is that and that it passes through the point 1,5. Do that, please. I hope I didn't give it to you. I did not. Okay, good. Oh, so good. Feel free to check with your neighbors once you have an answer. The drama is always fun.
I think we're solving 4fx But it says solve the difference. We're not finding the C.
Because this one
By the way, C is not 0. Okay?
you're probably
I was here, you were here, we were both here. How cool is it? All right, so C should be 7, yes? Okay. Now, the reason I'm going with C being 7 is because that pretty much puts all the puzzle pieces together. The odds of you getting 7 without taking the antiderivative correctly and or plugging and chugging is pretty slim. However, I did mention that C does not equal 0, and the reason I mentioned that is because a number of people did the following. Whoops. Let's try that again. Okay, so I take the antiderivative of f prime of x, which would be the antiderivative of 9x squared plus 4x minus 7 dx. Okay, look down real quick. Did you include the dx when you were writing your integral? If not, include it. If you're feeling fancies in your pantsies too, you can throw some parentheses around that, but not mandatory. Okay, I'm pretty good at this. So I would get 3x cubed plus 2x squared, and this is what caused some problems for people, minus 7x equals f of x, and I forgot the plus c. How'd I do? Yes? All agree? Good. What do I do next? Plug and chug. Put 1 in for x, put 5 in for f of x, solve. C turns out to be 7, which is what I think everybody got. And then my final particular solution, 3x squared plus 2x squared, 3x cubed plus 2x squared minus 7x plus 7, and I'm done. That is a differential equation. Same thing as finding a particular solution, just a different way of framing it or denoting it. Any problems? Your brain still might be stuck on derivatives. So you want to keep subtracting a number from the exponent. You want to take that exponent and multiply it by the number out in front instead of dividing it or taking it by multiplied by the reciprocal. You'll get better as you continue to practice. The farther we get away from derivatives, the better this will be. And then, of course, we're going to come full circle, and we're going to start doing derivatives again. That's where things will get really challenging. Questions on this? We're good? Close. Oh, I skipped that last one. Do we need to do another one? Sure. Okay, so okay, hold on there. Slow your roll, boss. All right, so let's suppose that we were going to do this. What do you notice the difference is between this problem and that problem? Babe?
It's double prime.
It's a double prime. But what does that mean? That means I'm just going to do the whole process twice. What happens when I take the antiderivative of f double prime? What do I get? F prime. And then I take the antiderivative of f prime and get f. The goal of a differential equation is to get back to f. When I take the antiderivative of f double prime, I'm going to get f prime, which means at first step, I would use this chunk of information. Then I take the antiderivative again. I'll end up at f, and then I would use that chunk of information. Okay, there's nothing new here other than doing it twice. If you want to work on it, knock yourself out, but I don't necessarily want to take the time. I would rather talk about what it takes to kill a kidney. I have about 4 or 5 of these. I'll put them up on a regular basis. Don't do that anymore. And I say that because some of you have been doing it quite a bit. Pregunta. That's Spanish for question.
Yeah.
Sí.
See. I can't do the rest in Spanish.
Bien.
So for the thing where it has 2 primes and you define the, so you end up, f prime ends up being something plus c. So when you go, you do another antiderivative, would you end up having like c times x?
Oh, excellent question. Okay, so give me 30 seconds and then I'll cut you loose. Liam just asked a great question. I have to do an antiderivative twice. When I do an antiderivative twice, am I going to generate 2 c's, and isn't that the same c? There's a couple different ways you can handle that. And your textbook, EP test, they handle it 2 different ways. When you do the antiderivative initially, you might get a plus c, blah, 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 plus c, and then you do it again. They will handle it 2 main ways. Number 1 is they'll call that C1, and then when you do it again, blah, 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 plus C2. That's one way. Not my favorite method. What I do is just change the variable. So what I like to do is do yada, 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 plus C, and then blah, 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 yada, 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 plus D. Just change it into something different.
Okay.
Try to avoid using letters like X and Y, because that just confuses.
But it wouldn't be like c times x, even though in the first one it was like.
Oh, okay. Now you're asking a whole different question. When I do this initial problem, let's keep it simple here. Let's suppose I have f prime of x is x squared plus c. If I use this initial condition, I can figure out what c is, and then I continue on from there. But just for giggles, let's suppose we didn't have this. If I do this, I need a dx over here. What's the antiderivative of c? No. The derivative of c is...
CX.
No.
0.
No. Let's do the easy one. What's the antiderivative of x squared?
3x cubed.
No.
1 over 3x.
1/3 x.
1/3 x cubed. Okay, good. What's the antiderivative of c? With respect to x. Cx. Very good.
Yeah.
And then you do plus d or something.
Then plus d. Okay. Who's confused? Remember, c is just a number. We don't know what the number is, but it's a number. And when you take the antiderivative of a number, it's... I don't know if this is going to confuse... I'm going to try it anyways. I'm sorry if this confuses you. Why is the antiderivative of 2dx equal to 2x? Okay, this is kind of going far down the rabbit hole. Some of you may want to put your fingers in your ear and just sit there and go, la, 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 for the next couple of minutes. But this is the same thing as that. Right? Because what's x to the 0? 1. Why would I ever write that way? I wouldn't, but I'm showing you why this becomes 2x. Raise the power by 1. Well, 0 plus 1 is 1. Multiply 2 by the reciprocal of 1, which is 1. And you get that. Oh, sorry. Okay. That's why when we take the antiderivative of constant, you just stick an x on the back of it. Take the antiderivative of a constant, you just stick an x on the back of it. That wouldn't happen in this problem, though, because you have initial conditions. Okay. Good. Any other questions? Liam?
So the solution to that wouldn't be differential direct, like, because you.
No,
only
because
want-
I would,
'cause you
once
only-
I took the antiderivative of this, I'd plug in 0, 2.
Yeah, but like you don't have a second initial condition for D.
Correct.
So
So I would use this then to solve for the D part in the second part. The second antiderivative.
oh, it also gives you I see.
Yeah.
That makes sense. I didn't okay, that makes sense.
Okay, that's all I got for you. What do I need? I need to close this.